Welcome back to trigonometry. Today we're going to still be talking about vectors as we have in previous recordings, but now we're going to be focusing on some applications of vectors. And for those of you who have this little nagging feeling in the back of your head about the word applications, yes, let's get it out of the way. Let's put it up front here. These are word problems. But what I'm going to do is go through some example word problems with you and go through and talk you through how to set them up, and hopefully after we do a good handful of these, it'll help you to get some ideas about how to set other word problems up too that involve vectors. Okay, so first example we're going to look at involves, let me define something first. It involves something called an equilibrant. An equilibrant is an opposite vector that counterbalances a resultant vector. So it's the opposite vector of a resultant vector. So like if you have a resultant vector that's u, the equilibrant would be negative u. And the equilibrant is going to be the subject of our first word problem here. Okay. This first word problem says, find the magnitude of the equilibrant of forces of 54 newtons and 42 newtons acting on a point A. Okay. It helps to know that the angle between the forces is 98 degrees. So 98-degree angle between the forces. And then you're going to also find the angle between the equilibrant and the 42 Newton force. Alright, now to get this set up, I find it good to draw a picture, just to see what's going on here. Okay, so we have two forces. We've got one that's 42 newtons and one that's 54 newtons. Okay, so that's going to be my two forces. Alright, and I'll go ahead and label this one as the 42 newtons. And then this one's going to be my 54 newtons. Alright, and then the resultant vector is going to be somewhere in between there. And then the equilibrant is going to be opposite of the resultant vector. Sorry, I didn't do that. My pen got stuck on my pad here. So that equilibrant is going to be opposite direction in the same. This was the resultant vector. This is the equilibrant. It's going to be the opposite direction, but it's going to have the same magnitude as the resultant vector. It cancels out or balances out that resultant vector. All right, and then we're told that these forces are acting on a point A right here. And we're told that the angle here is between the two forces was 98 degrees. Okay, so we need to find, like if this is the resultant vector v, then this is negative v. We need to find the magnitude of the equilibrant. That was one of the questions it was asking. So we need to find the magnitude of this, but if we find the magnitude of the resultant vector, that will be the same as the magnitude of the equilibrant. So we can work with that. All right, couple things here. Let's see. You can always draw a nice little parallelogram sort of deal. Now forgive me, my drawings aren't perfect, but at least they'll give you some ideas about what's going on. And you know opposite sides are going to be the same. Now if this angle is 98, that means this angle here these two angles have to add up to 180. So that means this angle here must be 82. And we know angles opposite each other are the same it makes this nice little parallelogram here. So this one's also 98. Alright. Now we know we have a triangle here. We don't know what this 98 degree angle, we don't know what it divides up into. These two angles here, we don't know what they each are, but we know the sum is 98. This resultant vector does not necessarily bisect the angle here. So we can't just jump to conclusions and say, oh, we got 49 and 49. If the two forces were equal, then sure, it would do that. But they're not. So this is not going to be a bisector here. So we can't assume anything there. But what we can do is we can look at the fact that we do have a triangle here. And we know a side, an angle, and a side. And then we can use the law of cosines with side, angle, side, and find the resultant vector length, this side here. So apply the law of cosines, and it can help. So the magnitude of the vector v is the length of this side of that triangle. That squared, according to law of cosines, is going to equal the 54 squared plus the 42 squared minus 2 times 54 times 42 times cosine of the 82 degrees. Okay, so you're going to put all that in your calculator, and you're going to get that the magnitude squared equals, and you're going to get 4,048.710814. And don't forget to make sure you're in degree mode, because our angles are in degrees. And then do the square root, take the positive square root because we're dealing with length. And you're going to get 63.6294807. But you can go ahead and say that the magnitude is around 64 newtons. So that's the magnitude of the equilibrant. Also. So that's the magnitude of the resultant vector, but it's also the magnitude of the equilibrant. So that answers this question. And then next, what's the angle between the equilibrant and the 42 Newton force? Okay, here's the 42 Newton force, here's the equilibrant. What is this angle here? Okay, so trying to find that angle. Well, If we go ahead and find x here, if we go ahead and find this angle, we'll call it, well, I don't know, I'm trying to find some nice colors to work with. Okay, if we call this, we just call this angle x. If we try to find this angle here, angle x, then we know that 180 minus x will be this. And I have more hopes of finding x right now than I do the question mark because of working with triangles here. Alright, trying to find x, I can use law of sines. Because I now know what this resultant vector length is. I know that it's 64 newtons. So I've basically got this triangle here where I've got this is 64, this is 42, this is 54. I've got 82 degrees here, and I'm trying to find x. Well, I can say sine of 82 degrees, law of sines, over 64 equals sine of x over 54. And I'm going to get that x is 56.67197,128. And then to get the question mark, I can do 180 minus x. And I'm going to get around 123 degrees. So I could say that roughly, that angle is around 123 degrees. And now you've answered both questions, because the other question was the angle between the equilibrium and the 42 Newton force. So you end up using law of cosines and law of sines there. So those oldies but goodies. We have some previous podcasts on law of sines and law of cosines, so if you're rusty on those, you're going to want to go back and refresh on those podcasts and working with those two laws. All right, moving on. Question 2, another type of question. Find the force. I feel like I'm in Star Wars. Use the force. No, find the force required to keep a 2,500-pound car parked on a hill. Make sure that parking brake works, right? Parked on a hill, or maybe you have just really strong rope holding it there, that makes a 12-degree angle with the horizontal. Okay, so in this one, I'm not a very good artiste, but just bear with me. Alright, I'm going to draw a hill. I'm going to draw a horizontal. And I have a little car parked on this hill. Okay. And we want to make sure this car stays parked nicely here. Now we've been told that this angle here is 12 degrees. That's the angle. We got the hill. The hill makes a 12-degree angle with the horizontal right here. Now we know that the car itself is 2,500 pounds. So we've got this 2,500 pounds dealing with gravity. Now, if it's 2,500 pounds, that means there's 2,500 pounds. That has to do with the force of gravity, pulling straight down to the ground where the horizontal is. Now we have what else do we have? We have a force acting on it, basically pulling on it in this direction to keep it from rolling down the hill. So there's a force pulling this. We got to figure out what that force is. That's what our unknown. So this is our unknown, but that's keeping it from rolling down the hill. So we have that. And what else? We've got a force in which the weight pushes down on the hill. The 2,500 pounds there has a force, with the weight pushing down against that hill. So let's also draw a vector where, that car, the weight's pushing straight onto the hill. Like that. Alright. Now if we take whatever that force vector is, we can translate it and put it over here instead. Now I didn't do a very good job drawing this earlier, but this force vector here is going to be the same as that one. So it's not very big. So maybe I should do a little erasing so it looks a little more the same. Let me redraw it. Let me redraw the hill there. And then that force vector is going to look more like that. Oh, my little tires disappeared. There we go. Okay. So this vector here is the same as this vector here. Remember, with vectors, as long as they have the same direction and same length, you can move them around on your page to whatever suits you. Alright, and essentially we're forming a nice right triangle here. We're going to end up having to work with that some. So let's do a little bit of labeling. Let's label this point here E. Let's label this point here B. This is just for convenience because the text I'm currently working out of uses these labels, so that's what I'm going to do. F. Right here we got D. Right here we got A. Right here we got C. Okay. So if we look closely, we've actually got two triangles. We've got this right triangle here. It's an obvious one. And then we've also got the right triangle here. It's another kind of obvious one. But what's not so obvious right away is the fact that these two right triangles are similar to each other. Okay, you might be like, what? They don't look similar. And when I say similar, I mean the angles are the same, sides are proportional. Well, let's look at this a little more closely. The ray BF and the ray AC are equal. All I did was just take BF basically and move it to here. But these two are, you can kind of move them around. But also, since they're equal, they're parallel to each other. So that's helpful. Ray BC plus, so you've got ray BC here, plus negative AC. See, normally you would have BC plus AC equals this, but the AC is actually pointing that direction, so plus negative AC, when put together, equals ray BA. So that's helpful to know. Just kind of going through looking at some of these relationships. BF and AC are parallel, so just also know that about those. Let's see. Knowing BF and AC are parallel, angle EBD, so angle EBD, this angle right here, measure of angle EBD equals the measure of angle BAC, which is right here. You might be wondering, well, how the heck do you know that? Well, if BF and AC are equal, their magnitude's the same, they're facing the same direction, they're also parallel. Well, if they're parallel, we can work with things like ray BA is like a transversal cutting through two parallel lines. So we have alternate interior angles. This angle and this angle are alternate interior angles. And that's how we know their measures are equal. They're congruent angles. So we've got two triangles here where we've got right angles, and then we've got these two angles are congruent. So if that's the case, if two of the angles are congruent, then the third one must also be congruent. So triangle EBD, it's the green one, you know this angle here is 12 degrees. And if that one's 90, you got 102, then this here must be 78 degrees. And then the other triangle, I'm going to draw it a little straighter so it's easier to look at. But triangle ABC, this angle is congruent to that angle, so this one's 78 degrees. And then this angle is congruent to that angle, so that one's 12 degrees. I knew about B and A. I knew about this angle here being congruent to this angle here because of alternate interior angles. And then from there, they must have the third angle also congruent if they already have two angles congruent in the triangle. Okay, so that's good to know. Now that ray BA was 2,500 pounds, that was like due to gravity. So we can go ahead and label that with 2,500 if we want. I don't know if you did that already or not. But what we're trying to find the force. We're trying to basically find the magnitude of AC here. I'm trying to find this. Because remember, that vector is equal to this vector, and this is the force vector keeping the car from rolling down the hill. So if we find the magnitude of that vector, then we've got our answer. Because we're trying to find that force required to keep that car parked there. So again, recap, ray BA is the 2,500 pounds gravity pulling straight down. Ray BC is the weight pushing on the hill. And then ray BF is that force that would pull the car uphill. And that's what's keeping it parked so that it's not rolling back down the hill. So we're basically trying to find ray BF there, which is also AC. So if we find the magnitude of AC, that will be the magnitude of the required force. Okay. So back to the math. If we look at this triangle, and we're basically trying to find AC, we can use the law of sines to help us out here. The sine of 12 degrees, or not even law of sines, just sines. The sine of 12 degrees is going to equal the magnitude of AC over that 2,500. Ooh, it's even easier. You don't even need law of sines because it's a right triangle. So just use the fact that sine is opposite over hypotenuse. Yay! Alright, so then the magnitude of AC is going to equal the 2,500 times the sine of 12 degrees. Make sure your calculator's in degree mode. Don't forget that part. You're going to get this crazy decimal, 519.779227. But you can go ahead and round that and say a force of 520 pounds would keep the car from rolling down the hill. All right. Okay, next one. Third one. On this one, a force of 18 pounds is required to hold a 74-pound crate on a ramp. So a force of 18.0 pounds is holding a 74.0 pound crate on a ramp. Okay, so we're dealing with the same kinds of forces we were dealing with earlier with the car sitting on the hill. What angle does the ramp make with the horizontal? So this time they don't give us the angle, we're finding it. What angle does the ramp make with the horizontal? Alright, so do some quick sketching here. We've got a horizontal, we've got a ramp. Okay, we've got a crate that's sitting on there. Some kind of wooden crate. Alright, and then we know that we've got a 74-pound crate sitting here. So we're looking at the whole gravity thing was 74 pounds, 74.0 pounds. And then we also know that there's a force of 18 pounds holding it on there. So 18.0 pound force. And we're going to translate that force to here. But remember, you can basically make a right triangle like that, because you got the force of the crate pushing onto the hill. 74.0 pounds was the force of gravity. You've got the force of the crate pushing down this way, and then the 18.0 pound force is the one holding it up so it doesn't slide down the hill. So that's that right there. You got 18.0 pounds. And the question's wanting to know, what is this angle here? It's wanting to know what that theta is. Alright, so we are once again dealing with some similar triangles. So we've got theta here, and we've got 74 pounds here, and then this is a right angle. Then let me redraw that triangle like this. We've got 18.0 pounds here. 74.0. Alright, the angles, let's see. This and this are parallel. The 18 pounds, those are parallel. So we've got, once again, alternate interior angles here and here. So this angle is congruent to this angle. So therefore this theta is going to be congruent here. That's going to be theta as well. Alright, and then we also know that this right here is 74.0 pounds right there. Okay. But you know what? If we find this theta, we're set, because that's the same as this theta. Now, if you look at this, we know the opposite side over the hypotenuse. We know that the sine of theta equals the 18.0 over the 74.0. If we put that in our calculators and do the inverse sine, theta is going to equal 14.0780386. So in other words, we go 3 significant digits because we have 18.0 and 74.0, 3 significant digits. So we're going to get around 14.1 degrees for that angle. Okay, next one. Next one's not a force problem, but rather a bearing problem. Ship leaves port on a bearing of 25.0 degrees. All right. It travels 61.4 kilometers. Then it turns due east and travels 84.6 kilometers. How far is it from port? Also, what is its bearing from port? Okay. Now, first thing I noticed was that when they gave us the bearing, all they gave us was degrees. So remember, this is, when they do that, the bearing is basically degrees from north in a clockwise direction. So we got to keep that in mind as we sketch out our situation here. All right, so we've got draw a little segment here. So we've got port, we'll call it P, or port. And then up here, this is due north. And we're being told that the ship is leaving that port on a bearing of 25 degrees. And travels 61.4 kilometers. Alright, so we'll draw that to there. So we got a bearing of 25 degrees, so in a clockwise direction from north, we're at 25 degrees. And travels 61.4 kilometers. Then at that point in time, it starts traveling due east. And when it does that, it travels 84.6 kilometers. So we have to figure out how far from port it is when it's finished. Oops, I don't want a purple, I want a black. I'm just being picky that way. Alright, so we're trying to find out how many kilometers it is now when it stops here. So how far from port is it? And then we're also wanting to know what is its bearing from port. So how many total degrees is that? Alright, so let's first worry about how far from port. That'll be important. Alright, if we look at this is a right triangle right here. And if we know that this angle here is 25 degrees, and if that has to be 90, that gives us 115 so far. So that tells me that this one here must be 65 degrees. Okay, so that's good to know. And if that one's 65, these two make 180 total. So this one must be 115 degrees. Alright, let's see, is that going to help us? Yes, it is, because we can use the law of cosines. Woohoo! That question mark there, the magnitude of that vector squared is going to equal the 61.4. We should probably do this. Alright, 61.4 squared plus 84.6 squared, I'm using the law of cosines, minus 2 times 61.4 times 84.6 times the cosine of 115 degrees. Woohoo! So you put all that in your calculator, and you're going to get 15,317.65041. Square root that, you're going to get 123.76447644957. Now we're going to go to three significant digits because you have 61.4 and 84.6. Those are three significant digits. So we're going to round to 124 kilometers. Alright, so now we know how far that is. Now we know how far from port it is. And then to get its bearings, well, let's see here. I know this angle and its opposite side. If I can find this angle, x, because I know its opposite side, then I can add that to 25 and get the total bearing. So I can use the law of sines here, because I know an angle and its opposite side, and then I'm trying to find this angle, but I know its opposite side. So I can say, alright, sine of 115 degrees over 124 kilometers equals sine of x degrees over 61.4 kilometers. And then, solve for x there. You do that, you're going to get that x is 26.66470.174 degrees. And then for the bearing, you're going to add 25. Let's see here. You're going to take that. Okay. And then, wait a second. Sorry, I have a really bad labeling here. If I call that x, this is like y. Sorry about that. Alright, so finding x, I was able to do that because I knew 84 point sine of 115 over the 124 is going to equal sine of x over the 61.4. And then that gives me this angle, but then if I know that's 26.66, etc., I know that's 115, then y here must be 38.33529.826. So then the bearing's going to take that angle and add it with the 25, and so you're going to have 25 degrees plus 38.3 degrees, and that's going to equal 63.3 degrees. And that means it's 63.3 degrees in a clockwise direction off of north. And that's the bearing. So I apologize for that, backtrack a little bit. When I was doing this, labels were bad, I was pointing to the wrong thing. I knew, when I was doing this, I took the angle of 115 and used its opposite side, 124. And then I was using, since I was using the 61.4, I was actually finding this angle. That should have been labeled x. Sorry about that. And then I was going to label this one y. So once I found x, I knew 115 and I knew the 26.7 basically. So those two, when you add them together, give you 141.7. So you subtract from 180 to get this one, and you get 38.3. Well, just finding that angle is not enough. Once you get that 38.3 degrees, you have to add it to the 25 that exists here to get that full bearing of 63.3 degrees. All right. Let's do one more question, basically involving bearing. This one's going to have bearing and airspeed. You have a plane that's on a bearing of 70 degrees. It's flying around. It's on a bearing of 70 degrees. But it has an airspeed of 230 miles per hour. It's going to encounter some wind. There's a wind blowing at 25.0 miles per hour. From a direction of 290 degrees. You want to find the resulting bearing and ground speed of the plane. Alright, so I have these axes here. I have this plane on a bearing of 70 degrees. So I'll put that there. I know that's not entirely accurate drawing, but that'll have to do. So bearing of 70 degrees and an airspeed of 230 miles per hour. Okay. So after an hour it'll be right there basically. Now this plane is encountering a wind of 25 miles per hour from a direction of 290 degrees. Alright, if we look at basically the wind bearing of 290 degrees, we go around, we got 90, 180, 270, 290. It's coming from that direction. Let's do this. Coming from a direction of 290 degrees. Like this. So if we move the vector, it's going to be hitting the airplane like that. And then it's going to affect the plane. So you could put a vector here, like you could put that vector here basically. Alright, so it's taken this one and we can move it to here. Now the resultant vector between the airspeed vector here and the wind here, the resultant vector we can get from that blue one, that's going to give us the ground speed. Okay, so we got to work on finding out more about this ground speed vector. Okay, so essentially we have a big triangle here. Let me just kind of re-sketch the triangle. Alright, we know this is this one's 230. Sorry. And we also know with the wind being 25 miles per hour, we know this is 25. And then if we're trying to find x, the ground speed, I just took this triangle here and rewrote it right here. So I'm going to go ahead and call the ground speed x. Alright, I need to be able to figure out some information about angles and things too before I can do much with trying to find that ground speed. Like, if I know this angle here, I know what that is. Maybe I can do something more with this. Like, if I know what that is, I can use law of cosines to help me solve for x. And let's see, can I find that? Well, let me draw some new axes right here. Whole north, south, east, west axes. If I do that, essentially the x-axis here, the east-west axis, is parallel to the east-west axis here. The north-south axis is parallel to the north-south axis. So I might be able to use parallel lines to my advantage. Let's see here. If I know... Ooh, alright. If the north-south axes are parallel to each other, then this vector is kind of it's basically a transversal. So that tells me that if this angle is 70 degrees, this one here has to be 70. Because of alternate interior angles, if these two are parallel. What else do I know? Let's see, if I know that's 70, I know this here has to be 20. Not sure that's going to really help, but I'm just, trying filling in some stuff that I know. Maybe that'll lead me to things. Ultimately, I need to find this full angle here. Can I do that? Well, if that's 70, I know this here has to be 20. So then I know, let's see, I know then that, I knew that's 20. If this is 20, that's 20. What about, let's see here. What else do we know is 20? Let's see, if we extend this, these two, the red ones, are parallel. Does that tell us anything? I gotta figure out what this is. Can I? If that's 70 and that's 20, I knew this one was 20. I know this one's 20 because all the way around is 290. This has to be 20. This angle here. So with the wind, well, the wind is at this vector and this vector are equal, so they're going to make the same angles with the axes. So that tells me this right here has to be 20. And that would mean this is 20, which then means that this has to be 70. And you see that? Like, you have the north-south and east-west axes, and then you got the wind vector. We know it's making, if we know it's 290 all the way around, then this has to be 20 here, because going just 3/4 of the way around is 270, and an additional 20 would make 290. Well, on this axis system, it's going to be the same angles. It's going to be a 290, so that means this has to be 20. And then by vertical angles, if this is 20, that's 20. By right angle, if that's 20, this has to be 70. Ah, so that tells me that this total here is 140, and that's exactly what I needed. I needed the 140. Because then I can use that. I can say, well, x squared equals the 230 squared plus the 25 squared minus 2 times 230 times 25 times the cosine of 140. Woohoo! Put that in, you get x squared equals 62,334.5111. Do the square root, you get x is 249.6688.028. So basically, that ground speed, x, is around 250 miles per hour. All right, that's the ground speed. Then next, to get the bearing, what do we do? The bearing, I basically need to know what this here is. I don't know what that angle is. But you know what? Sine of 140 over 250 will equal sine of question mark over 25. You can use the law of sines. Put that in your calculator, you'll get that the question mark equals 3.685442587 degrees. But that question mark is just this angle here. Add that with the 70, and you get that the bearing, basically this rounds to 4 degrees. You get the bearing is 74 degrees. Because you just found that this is 4 degrees here. So you got the 70 plus that 4 to make that whole thing 74 degrees. All right. Well, that's enough examples for now. Please, make sure whatever lesson in your book has the application problems. Practice these a lot, because as you see, problems like this can take some time to think through, but as you practice them, you're going to recognize the patterns and start to see, what exactly it is you need to find. So, happy trig!